So yesterday we covered until this farming digital farming food multiplication. Next we are going to cover sequential circuits. Uh, Sequential circuits. Like there are two types of circuits, combinational circuits. Like if it is in a half adder here, input half adder, output here, if here is separated, half separated, input, output. So multiplex, if there is a multiplexer, the input goes and output comes. If there's a decoder, the input goes and output comes. But in a sequential circuit, the combinational logic, input plus previous state gives the output. So this sequential circuit has a memory other than uh, combinational circuit. Sequential circuit has a memory. Input combinational logic, output memory. The memory is provided by the flip-flops. Why do we need a clock? Most sequential circuits use a clock signal to control when their state can change. State changes. The circuit may change its stored state at the appropriate clock age, clock timing reference signal. Sequential circuits I already studied this. Counter sequential circuits. 4 bit plus means 4-bit register. Shift register, next class. So I am series in the series out. It just means if four bits come, the 4 bits go in series. If 4 bits come, then the 4 bits go in parallel. If they come in parallel, they go in series output. 4 bits. People parallels come and parallel will go. 1 bit at a time. Series means 1 bit at a time. Uh, yes. Multi-bit switch simultaneously will go. Series means 1 bit at a time. Let's see. So means series in series time. 1 bit attends at a time, 1 bit leaves at a time. That's why it is called series. Means if you send 4 bits, 4 bits enter at a time. Like 4 bits one, the next will come, the next will come, and see 1 bit at a time enters, but after several clock pulses, you can read all bits simultaneously. So 1 bit enters a time, but after several uh, clock pulses, we can send out them simultaneously, parallel in series or multiple bits are loaded together and then shifted out one by one, parallel in series connection. Parallel out, all bits enter together and all bits leave together, useful for me. This is, I read it in a different way. Okay, look at the diagram. So this is this so parallel input. The output input gets parallelly and the series of output gets 1 bit by 1 bit. Here if you look at the system, series in out, series out, data is in uh, entering in left to right, data is going left out. So it will this is something like they can move left to right or right to left. That's what it's saying. Okay. flip-flops, uh, input, here it is input, here it is output, here it is output, 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 parallel data output, you see, this is parallel data output, here series data input is given, then parallel data output is going. This is clock. I think this is clock pulse. Okay, this is clock pulse. Here it is one bit at a time. Okay, so I already read all this. We will go into control system. It is simple to understand. As I already read these two, I will tell you what are these. Open loop system means there is only input and output. There is no feedback going to the input again. Here feedback means the feedback comes from a microcontroller or something like that. The example is if you drive a car, it's going at a speed, you want to change the speed again. When you change the speed, the output from the microcontroller or something like that in the car will measure the speed and give it to the input again. So will measure the speed and if there is any and subtract it with the output. So you get a value and it will add it to the input so that your current speed and the other your desired speed you want to go will come after the input is added from the feedback to the original speed. That is called that is a closed loop system. Okay, I was talking about closed loop system. Your open loop system doesn't use any feedback. It simply functions like the input comes, it will give the output. It simply functions like that. It doesn't care. It doesn't do any feedback, anything else. Signal flow graph. I think I don't know. Stability means there are some values. If all poles are LHP stable, what is stability? Actually, I computed these three. I don't remember this. Signal flow graph. I don't remember. Stability. The basic question is: if we disturb the system slightly, does its output settle down or keep growing? Stability. The basic question is: if we disturb a system slightly, does its output settle down or keep growing? So it should be settled down, right? It shouldn't keep growing. To disturb the system slightly. Imagine a system receives a small disturbance, stable. The output eventually settles, like oscillates die away and stable output remains bounded. Unstable, the output keeps increasing, means is not stable, failed. It's a system is failing. Like output, desired output is not coming. Unstable, output becomes unbounded. Marginally stable, the oscillation continues at a constant amplitude. So it either grows nor dies. It keeps increasing, reducing, increasing, reducing like that. Why do we care about poles? This is the important connection to a logarithmic network function. Poles and zeros topic for a continuous time system. The location of the poles determines stability. Suppose the characteristic equation gives poles s equals to minus 2, s equals to minus 5. Both are on the left side of the plane. S equals to minus 5, s equals to minus 2. Both are left side of the plane. These produce decaying responses. Therefore, all poles in the left half of a S plane is stable. Right half plane. If s is equals to plus 2, that's on the right. The right half plane pole produces an exponentially growing component. Therefore, an RHP pole is unstable. Pole on imaginary axis, for example, s equals to plus j2. This gives sustained oscillation. For the basic case of simple poles of imaginary axis, all other poles in the left half plane marginally stable. Repeated pole on the imaginary axis leads to instability. If you take an axis j omega, this is left plane and this is right plane. Like it is a Christograph graph, like Christian graph. Here minus or minus 2, these two are in the left plane. Left plane means they are stable. If the values come into the right plane, they are unstable. And if the values are like fluctuating means j is an imaginary, imaginary axis. So it is marginally stable. That's simply to understand. It's simple to understand. This is the foundation of Rhodes equation. Characteristics. Why do we need rocks? Suppose your characteristic equation is s power 4, 3s power 3, 5s squared, 7s plus 2. You could solve the polynomial and find every root. But that's tedious. Roundhouse gives us a systematic way to determine how many roots are in the right half of the explain without actually solving for all the roots. So next we'll learn the routhwitz criteria. Okay, we'll come later. Well, so absolutely routhwitz criteria. We already established tables so all poles must lie in the left half of the explain. The problem is that finding the poles means solving A and exponent equation here. For a high order polynomial, solving the equation can be different. Routhwitz, which gives us a shortcut. It tells us whether the system is stable without calculating the actual root circle. Start with the characteristic equation, suppose x1 plus 2x2 plus 2x plus 1 plus 2. We arrange the coefficients in a root array. The first two rows are made directly from the polynomial coefficients. Uh, S cube is 1, for S cube it is 2, and for S it is 3 and 4. Why? Because S cube plus 3S cube plus 3S plus 4 has coefficients 1, 2, 3, 4. We alternate them. S cube has 1, comma 3 and S cube has 2, comma 4. Calculate the next row. Now calculate S for own row. Then the formula 2 into 3 minus 1 into 4 by 2 is 60 minus 4 by 2 equals to 1. So S cube is 1, 3, S2 is 2, 4, and S1 is 1. Then as the S4 0 is simply 4, the complete table is S2 plus 1, 3, 2, 4, and 1, 1, S0, 4. The most important part, look only at the first column. S cube is 1, S square is 2, S1 is 1, S0 is 4. So 1, 2, 1, 4. There are no sign changes. Therefore, 0 right hand plane rules, so the system is stable. The golden rule, this is the part you should memorize. Number of sign changes in the first column equals the number of right half plane rules. Therefore, no sign changes, stable. Assuming there are no special cases and the system is properly formed, sign changes, the system is unstable. Is, for example, first column plus plus minus plus. Look at the transitions. Plus is plus is minus, minus is plus. Quarter 2 signs change, therefore 2 RPS tools and the system is unstable. Next is slightly better example. Consider s cube plus 4s square plus 5s plus 2 equals 0. First two rows s cube 1, 5. S cube is 1, comma 5. S square is 4, comma 2. Calculate s power 1. 4 into 5 minus 1 into 2 by, like 4 into 5 minus 1 into 2. Cross multiplication by 4 equals to 20 minus 2 by 4 equals to 4.5. Then these four values, so it is divided by 4. First column 1, comma 4, comma 4.5, comma 2, all partial no sign changes, therefore stable. Another example, whether it's stable s2 plus 2 s2 plus x plus 10 equals 0. Row table s2 1 and 1, s2 2 and 10, calculate 2 into 1 minus 1 into 10 by 2 equals minus 8 by 2 equals to minus 4. So s3 for first column, sign changes, 2 sign changes, so 2 are which zeros unstable. So it gets minus 4. So why did he do by 4? That's the question. Where he, in the second example, he done by 2. So he is using a square value. 2. Here also he used a square value 4. A square value 4. So he divided by 4. This is completely new to me. Here also he used a square value 2. This is the equation. Whereas calculating x1 row, my doubt is how did he get this set? How did he put x cube in 1, comma 3 and x square is 2, comma 4 by saying the equation? I don't know the root theorem, so I don't know how we will arrange it. The root theorem itself first. Start with the characteristic equation. Suppose x cube plus 2x square plus 3x plus 4. Look the power of x. X cube x square x power 1 and x power 0. X cube is 1. Square is 2, x power 1 is 3, x power Now we arrange them in a row chart. The first one is S cube. Take the quotient of S cube, then split one quotient, then take the next. That's the thing. We should take the quotient of first figure. If the next quotient, then the second group, that's the root error. Because the quotients are 1, 3, take 1, 3, this is the root error. The second row S cube, take 1, 3, this is root error. That's the key pattern for S cube. We have quotients 1, 2, 3, 4. We are basically alternating the same between two cases. Now we calculate it from the first two rows. The formula for the first element of the next row is 2 into 3 minus 1 into 4 plus 2 into 3 minus 1 into 4 by S square quotient. Second row first. Like we use the second row first, first row second, first row first, second row second, by second row first. Yeah, by the root array, second row first row first into second row second, second row first into second row second by first row second by second row first. That's the formula. So first we do second row first. First we do 2, 3, then only 1. Not like cross multiplication. Here 2 into 3, 4 into 1. Okay. Therefore, S cube we get 1, 3, 2, 4. As for one value we get 1. Here 1 comes. Then for S for 0 row, for the simple example, the final row is 4. The final row is 4. For example, the final row is 4, not this. If we see the root parent, the final row is 4 for the single. So 1, 3, 2, 4, 1, comma 4. I don't even understand. That's one root parent. Look at all of. So S0 is just. Let's slow it down. What is S0? The non-zero number rises to the power 0 is 1. So S for 0 is 1. If we have 4 S0, it's simply 4 into 1 equals 4. Therefore, 4 S for 0 equals 4. Why does S4 does not appear in the row terrain? Take out characteristic equation. This is S0, this is S1, this is S2, S3. So the powers are S3, S4. The last term 4 is actually 4S0. Okay. That's why we use 4. The S0 row simply corresponds to the constant term. Why did we calculate the S0 row? Look at the polynomial again. S cube, S cube, S cube. The 4 is already given directly in the original equation. So eventually the last row is S0 is 4. The root table is simply optimizing the polynomial from highest row to lowest. S3 first row, S2 second row, S1 third row, S0 fourth row, and S0 equals to 1. Okay. It is came because it is constant term. Why do we put S3, S2, S1 on the left? Because we are arranging the polynomial in descending power of S, S cube, S square, S1, S0. For a fourth order equation, S for 4, S cube plus BS square, CS plus G equals to 0, S for 4, 1 B D, S cube AC 0, notice the same alternating term. So S for 4, leaving the If we take as for coefficient 1, leaving this, it is B here, leaving this is G here. Now do the same with S3, it is J here, leaving it is C here, leaving this, it is 0, there's nothing here. Because it replaces nothing, it put 0. What is the same alternative? Here's an even easier way to visualize it as 2 square plus 3 square plus 5 square plus 7 plus 9 equals 0. Write the coefficients in a line 2, 3, 5, 7, 9. Not all. Take alternate coefficients. First row positions 1, 3, 5. 2, 5, 9. Second row positions 2, 4, 3, 7. Like 2, 4, 3, 7. So S power 4 is 2, 5, 9. S power 3 is 3, 7, 0. We put 0 because the second row doesn't. The easiest way to remember. I understand. For example, I understand question. If you continue, if you allow me the same thing again. So we get this value. There are no sign changes. 0 right half plane means it was stable. The golden rule. Number of sign changes is the first column equal to number of right half lines. Therefore, no sign changes. Sign changes. The system is unstable. For example, first row column. We get the same values. If one is negative value, look at the transitions. So look at these two. First plus, no change. Plus minus, there is a change. Minus and plus, there is a change. So two changes, that means two right hand plane folds. We only discussed right hand fold plane means it is an unstable. Let's do a slightly bigger example. Okay, these are all examples. This is a unstable. 1, 2, 1, 2, 2, plus minus, there is a sign change, minus plus there is a 2 had right hand plus. Why does this work? Remember what we learned? Okay. Although it doesn't tell us the exact location site, instead it tells us how many roots are in the RHP. RHP roots equals 0 when the system is stable. Providing the standard condition specifications satisfied the row stable pattern. Okay. Here the rules. Why should you remember for any telephone? For a stable system, all elements in the first column of the root are must have the same size. Normal positive with the characteristic polynomial is normalized with positive leading coefficient, number of signals in the first column, number of RHP roots at the half of rows for which there are special cases in the root table, especially when 0 appears in the first column and entire row becomes 0. Very important for exam problem, but they are easier to understand after you are comfortable with the normal. Now we should do 2, 3, root 3 and problem. Starting with the photo. I understand it won't be any the problem. I love that system. I don't right. Once you understand the Rothschild concept, you can see the numerical problem. Next, Nyquist criteria. So I completed this stability basic. Now, Nyquist criteria. Nyquist criteria, the basic idea, the which always looks at the explain code directly, but Nyquist takes a different approach. It studies how the open loop frequency response behaves around a particular critical point for a feedback system usually data L of x is equals to g of s at g h of s. G of s is forward open loop transfer function. H of s is feedback transfer function. Nyquist examines L of j omega as frequency changes. The critical point, the most important point in the Nyquist plot is -1 plus j naught j it's simply -1. Why? For a negative feedback system, 1 plus g of x into h of x equals 0. At the boundary of instability, g of x into h of x equals to -1. Therefore, critical point is imaginary and real. The Nyquist plot tells us that the frequency response curve encircles this -1 point in the required way. While this is useful, suppose we have a complicated system. Instead of solving its characteristic equations directly, Nyquist lets to determine closed loop stability from the open loop frequency response. That's the big idea with process Nyquist. Roots for which Nyquist uses characteristic equation over frequency response. Work in S domain using G omega counts RH to reverse encirclement of -1. Uh, algebraic method, this is graphical frequency method. So the question is essentially how does the curve behave the respect to critical point -1 plus 0? The exact instability conclusion depends on the number of open loop right hand side poles and the number of direction of encirclements. So the common case where the open loop system has no RHP pole system, simple intuition is no circle and no circular encirclement of -1 is closed loop stable, while an inoperative encirclement indicates instability. Don't memorize your full length mathematics set. So just look in this L of j omega equal to g of j omega, h of j omega, critical point is -1 plus j naught, stability of the encirclement. Then L of j omega means what? What is L of j omega? What is L of s? Nyquist examines L of s as frequency changes. What is L of s? Frequency. Critical point. This is a critical point. -1. Why? For a negative feedback, 1 plus g of s plus h of s equals 0, g of s equals -1. There are critical point -1, equals minus frequency reference for answer equals -1. Point in the required way. This is very useful a complicated system. What is L of v? How are you trying to stay from the critical point? Which critical point is stable? So you are very close. The concluding part is -1 is not stable point. It's a reference point using we to get the stability. Let's break it down. What is Lj all of j omega? We first determine L of s equals to g of s h of s. Where L of s g of s is formula for h of s feedback of. We solve the operator transfer function. Now we fix the substitute f equals j omega. So L equals j omega, g of j omega, h of j omega. Implement what is the gain and phase of the open system at a particular equals to omega. And omega changes the graph equal to time equals L of j omega changes the matrix that process those changing values of the complex case. So what is -1 point? Given the closed loop matrix of some negative feedback, T of x will be equal to 1 plus T of x over H of x. The denominator is 1 plus T of x into H of x, so the ratio can become unstable. The denominator can become 0, 1 plus T of x H of x, etc. Over the point with the other side, G of x is equal to -1. Since allow is into the HRS, we get allow has equal to minus 1, that's the minus 1 that we have is called the critical point. Okay. Is the critical point is stable? No. Actually, think of it as a danger point or boundary condition. It means L of j omega equals minus 1, which corresponds to magnitude in 1. Phase is minus 180. At that condition, the rating feedback can effectively turn it into a positive feedback at the frequency. That's why it is dangerous. Think of it as a warning light. Imagine you are driving safe area, danger point. The minus one isn't safe. It's a point we are watching to decline. As the system becomes unstable, all the vehicles to accelerate with after log omega. Or many frequencies for example have omega code 0 and omega star. Omega is 10 and omega is 100. Each frequency reduces a complex value. Those points make the call, then you ask for the next study and set to the critical point minus one way that is indicates instability. That's what the difference calculation is about. The easy to remember, don't think critical point is equal to think of a minus one danger as a constant. And open loop plus phase frequency. Yes, that's it. That's it. What he was trying to say. The critical point means a danger signal. And the love has equal to G of S forward plot plus feedback path. Now we replace S with S equals to J omega. So Allah it is a frequency now. Particular frequency open loop system. Here it is an path now. Here transfer function equation. This is a then here if we replace it, this is a frequency equation. Low frequency from to high frequency along with changes. The liquid stop drop the changing values on the concept place. So it is a minus one is a remember the previous test. P of x g of x, the denominator 1 plus g of x into h of x. This is where this is there, right? This denominator uh, to become unstable, the denominator can become a zero. So for this to get unstable, it needs to get zero. Move one to the other side. This is the danger point. He was telling. Equal point means danger point. Magnitude 1 and phase minus 180 degrees. Okay, what is next? We can move to bodplot. And don't get confused J0. That simply means like G of J omega. That simply means yes, it is an imaginary equation. For minus 1, J equals 0. J0. The yes, that's the bot plots usually and keep mathematics like a bot plot is a way of showing the how the system's moving magnitude changes its frequency, phase changes its frequency, so the reactive network loss bot plot magnitude dB phase degrees, the horizontal axis in both its frequency, usually on a lower 6-minute scale. The magnitude plot suppose an amplifier has G of omega equals to 10, we can express gain in decibels. Gain of decibel is 2 to 20 log 10. We have the omega base 10, for example, 20 log base 10 equals 20 dB. So gain of 10 equals 20 dB. Some useful values 0 dB to 60 10 is 20 dB, 100 to 40 dB. The phase plot. The sleeping plot shows phase shift introduced by the system. For example, 0 degrees might gradually become minus 44 degrees Celsius, it will become minus 90 degrees. Example, simple RC low-pass system construct input R and C ground output. The transfer function is g of s equals to 1 by 1 plus s r c put s equals j omega, then g of j equals to 1 by 1 plus j omega r c. Now watch what happens as frequency increases at low frequency. When omega is 0, then j omega c is 0, so g of j omega is equivalent 1 magnitude taken off the base 10 is 0 dB. The phase 0 to close. So low frequency gain is the graph between the gain and frequency 0 dB low. The circuit passes low frequencies as frequency increases. The capacitor impedance is Xc plus 1 by omega c as frequency increases. Omega increases, therefore Xc capacitance resistive capacitance decreases. This is resistive capacitance equation. Okay? Impedance. The capacitor increases channels the signal towards ground. So the output decreases, the magnitude ball plot starts falling. So from gain to it is getting to falling low frequency. For a first order low pass system, the slope after the cutoff frequency is minus 20 dB by a decade. So what is a decade? A decade means frequency increment by a factor of 10. For example, 10 Hz is to 100 Hz is 1 decade, and 10 Hz to 100 Hz is 1 decade. Also, 100 Hz to 1 kilohertz is another decade. uh, in 1 decade is 1 volt. So minus 20 dB per decade means the gain decreases by 20 dB every time. Frequency increases 10 after the corner frequency. So frequency decade means frequency increases by a factor of 10 means 10 into 10 is 100. 100 into 10 is 1k. Okay, won't get confused. It is 1k. So minus 20 dB decade means the gain decreases by 20 dB every time. Frequency increases by 10 after the corner frequency. Gain is decreasing by 20. This is not gain, this is frequency. The gain is decreasing 20 every time. After the corner frequency, it increases 10. It increases the decade. Every time frequency increases by 10. Cutoff frequency. For an RC low pass filter, RC equals to 1 by 2 by RC. At the cutoff frequency, gain magnitude of gain is 1 by root 2, which corresponds approximately to minus 3 dB. So the magnitude plot looks roughly like gain dB minus 3 FC minus 20 dB decade log of phase plot. Here j omega is equal to 1 by. So this is RC low pass filter. RC is 1 by 2 by RC. This is a formula 1 by omega RC. Sorry, 1 by 2 by RC. At the cutoff frequency, gain magnitude of gain is 1 by root 2. So he wants to tell which corresponds approximately minus 3 dB. Gain decreasing here. So the it is also minus 20 right. The gain is decreasing. So the magnitude plot looks roughly like gain is here decreasing minus 3. Decrease minus 3. Therefore frequency increases something. Yeah. 10. Therefore decades 10. For decade increases minus 20. Decade increases. For example, g of j omega equals to 1 by 1 plus j omega RC. The phase is the phase plot. G of j omega equals to 1 by 1 plus omega RC. The phase is phi equals to minus tan inverse omega RC. At very low frequency, phi is 0 degrees. At cutoff frequency, phi is minus 45. At very high frequency, phi is minus 90. So phase 0 minus 44 minus 90 SN log F. That's the bot plot of a simple low pass system. This is the bot plot. This phase plot. This is a bot plot. Why do we care about bot plots and contour systems? This connects directly to what we were discussing with Fish. Bot plots helps us determine gain margin, how much gain can influence before the system reaches instability. Phase margin, how much additional phase lag can occur before instability. There are important measures. Okay. So we stop here. Bot plot is a magnitude plot plus phase plot. Both are plotted against log frequencies and first order magnitude with phase eventually approaching minus 95. What to understand here. So bod is nothing but magnitude plus phase plot. Here we cut off frequency with with here on we will discuss magnitude. This is magnitude. Yours. Magnitude. Here, this is magnitude. 20 days less. The gain is 10. For digital geometer, we calculated gain dB equals to 20 log 10 both magnitude geometer. The value come from, then we solved it, we get 20 dB. So gain of 10 equals to 20 dB. Some resting values. One, these are to remember. You can remember this. I just leave it like this. Phase plot. The second plot shows the phase shift. So for example, 0 degrees might gradually become minus 45 and even to become minus 90. I think it is given example to understand we just look this what he was trying to say. Phase plot gradually becomes minus 45 introduced by this. Here it gets minus 90. Just leave all this. So here this is 0 minus 45 90. As it is decreasing for 20 days well. Here it is shown A and D between 20 days. This is the same thing. 20 days is decreasing. 80 minus 4 phase plot. Why do we care about bodplot in complex systems? This kind of this stream margin, phase margin. So bod is nothing but magnitude plot plus phase plot. Just remember like that. What's next? Continue. Use it to store online. Read teleconference because it is so long. That's why as bottlers, especially investigate among super large plots. I'm tired now. Let's stop here. We continue.